Hi everyone, Professor Burns here, and we're looking at the second lesson in our last unit, which is on a couple different ways we can solve systems of differential equations. Just like we've been doing all semester, of course, our goal has been to solve differential equations. So if we have a system, we need to have some methods for solving those as well. So I'm going to start off here with a little application here. So it says a common application of that second order differential equations is called the damped harmonic oscillator. And if we were in a physics class, we might use this a little bit more often, but I'm just using this sort of as an example of one way we can work with these systems of equations. So what we have here is m is a constant, b is a constant, of course k is a constant, second derivative, first derivative, and then y. So one way we can rewrite this, just divide everything through by m, and this system just becomes the second derivative of y plus b over m times the first derivative of y plus k over m times y equals 0. And this is kind of the standard way we might write this. So example 1 says, convert the damped harmonic oscillator to a first order system of equations. So right now it's a second order differential equation. We want to turn this into a system of equations in the first order. Y and v, of course, are dependent variables. So one thing I didn't mention here is that y is the displacement, just like it was back in Calc 1 or in your physics class. Remember, we have displacement, velocity, and acceleration. So if the first function they give you, in this case we'll say it's y, represents the displacement, the first derivative, remember, represents the velocity. Remember, I used to call it PVA when I taught Calc 1. So if y is our position or displacement, the first derivative would be the velocity. So that means that if v is my velocity, dy dt is going to just be v, right? Because the first derivative of displacement is velocity. So I'm going to write the system as dy dt, that's my first derivative, is equal to v. All right, what else do we know back here? That if dy dt is equal to v, then the second derivative of y with respect to t would be the derivative of v, or dv dt, right? Take the derivative of this expression, you get this. So how does that apply? Well, the second derivative of y, go back up to here. If we do some algebra and solve for the second derivative, then dv dt can be expressed as the rest of this expression. In other words, move all of this to the other side, and we get negative b over m dy dt, but I'm going to write that as v, remember, because that's what it was equal to, plus k over m times y. So what I've got now is a system of equations in first order. Both of those are first order differential equations in terms of y and v as my variables. And again, we'll see that sometimes it's easier to work with the systems when they're written as first order rather than second order, and that's the purpose of this. We'll do a little practice with this in class. Let's look at the next example. It says, consider the equation. So we've got the second order differential equation. Again, this is a form of the damped harmonic oscillator. It says, use the guessing method to find particular solution. So here's the way this works. First, we're going to make a guess. And it's going to be an exponential function, I'll tell you that. So it's going to be y equals e to the, this looks like a 5, but it's not, st. And so from there, take the derivative. So the first derivative would be s e to the st. And then the second derivative would be s squared, e to the st. Now substitute this into the differential equation. We end up with s squared e to the st plus 5s e to the st, and then plus 6 e to the st equals 0. And this hopefully looks familiar because this is what we've done previously in the course. We can factor out an e to the st, and what we're left with is the characteristic equation. And then this, of course, can be broken down. So make a note here if you want to, that this is your characteristic equation. So we can factor this as s plus 3, s plus 2. And the roots of that equation then become -3 and -2. So then you end up with two particular solutions. So your solutions then are going to be e to the, remember s is that the root of that equation, so it's going to be e to the -3t. And then my other particular solution is e to the -2t. And we'll talk more later about how to generalize this, but those are going to be particular solutions. Now the second part of this said convert this to a first order system of equation in terms of y and v. So what we did previously in the last example. Now before I jump in here, let's go ahead and identify a few things. So b over m is going to be that coefficient on the dy dt. So let's just kind of jot that down. B over m is 5 and k over m is the coefficient on y, which is going to be 6. So remember, using this format here, my system of equations is going to be dy dt is the velocity v, and then dv dt, remember, is the second derivative of y. So if we solve for the second derivative here, the 5 and the 6 go to the other side, and I end up with -5v minus 6y. And so that's going to be my system of equations as a first order system of equations. Now let's talk a little bit more about these types of systems. There's two types of systems here we're going to work with, and those are called a completely decoupled and a partially decoupled system. So what's the difference? A completely decoupled system is one in which each differential equation only depends on its own variable. So in other words, dx dt would only depend on x in the equation, and dy dt, for example, would only depend on y. A partially decoupled system is where one of the differential equations only depends on its own variable, and the other one can depend on both variables. So number 3 says identify this as either partially or completely decoupled. Well, notice that dx dt only depends on x, -2x, in other words, there's no y in that differential equation, and dy dt only depends on y, there's no x in that differential equation. So each one of these differential equations only depends on its own variable, which means that we're looking at a completely decoupled system. So when we have a completely decoupled system, it's actually pretty straightforward to solve because we can just solve each differential equation separately and on its own. So let me just start with dx dt. So dx dt equals -2x. Notice that this is just a separable differential equation. We can write this as dx over x equals -2 dt. Integrate, we get natural log of x equals -2t plus c, and I'm going to solve for x here, and I'm going to exponentiate both sides, so I get x equals, remember that c can move to the front because it's just e to the c, so that becomes c e to the -2t, and that's going to be my solution for that part of the equation. And then we can do the same thing for the dy dt. I'm going to go ahead and separate those variables as well. So I have dy over y equals -dt. We're going to integrate. We get natural log of y equals -t plus c, exponentiate. We end up with y equals c e to the -t. Now these are different c's, so I'm going to call this c1 and c2. They're different constants. If I had an initial condition, I would solve them, but I don't. So we're just going to write the general solution is going to be a system of equations. So x of t is equal to c1 e to the -2t. and y of t is going to be equal to c2, e to the negative t. So when you have, like I said, a completely decoupled system, you just work with each one separately, and it's no big deal. Then just put them together at the end. Now, what happens when we have a partially decoupled system? So let's make sure we're clear on what we mean by partially decoupled. Remember, partially decoupled meant that only one of the differential equations depended on its own variable. So if you look here, notice that dy dt, that equation, only depends on the variable y, whereas dx dt depends on both x and y. So this would be a partially decoupled system. So let's talk about what to do this time. All right, first we're going to solve the single variable equation. So in other words, dy dt equals negative 4y. I'm going to skip the details, but using what I did in the last example, separating the variables, we would get, here, let me write some of this down. Solve for the single variable equation. This would have been y of t equals c1 e to the negative 4t. Just separate the variables and you'll see what I'm talking about. Next, let's substitute that in to the other equation. So dx dt then becomes 2x plus 3y, but we just said y was this expression, so 3 times c1 e to the negative 4t. And recall from earlier in the course, the linearity principle said that a general solution, or an overall solution, we could think of it as the complementary solution plus the particular solution. So the complementary solution went with the corresponding homogeneous equation, and the particular solution went with the non-homogeneous equation. So let me go ahead. I'm going to rewrite. I'm going to solve this expression, this dx dt expression. I'm going to move the 2x to the other side. So I'm going to write this as dx dt minus 2x equals 3c1 e to the negative 4t. And then I'm going to guess the particular solution. So I'm going to just make a guess, kind of like I did earlier. And I'm going to say that a particular solution would be something in the form e to the negative 4t, but some coefficient that I'm going to call alpha. I don't know what it is yet, but I'm going to just call it alpha for now. So then I'm going to substitute this back in to that above equation. So dx dt, if this is my particular solution, dx dt would be the derivative of this expression. So let me come over here and write that. X sub p prime would be negative 4 alpha e to the negative 4t. So I'm going to substitute that back in. So I have negative 4 alpha e to the negative 4t minus 2x, but x we just said was going to be alpha e to the negative 4t, and that equals 3 times c1 e to the negative 4t. So my goal here is to solve for alpha. So we're going to solve for alpha. Notice that they all have e to the negative 4t, and I can combine like terms. So I wind up with negative 6 alpha equals, because the e's would divide out, 3 times c1, and then alpha would be negative 1/2 c1. And that's going to be what I'm going to use in my general solution. So let's put all this together here. So my general solution is going to look like this. X of t is going to be my complementary solution, which, by the way, I'm not sure I said that earlier, this x sub c, that's just using the 2x, remember, just the homogeneous differential equation. That would be e to the 2t. So let's write that. It's going to be c, I'm going to call that c2, e to the 2t, minus my particular solution, or plus my particular solution, which is right here. So let me write that. X sub p would be negative 1/2 c1 e to the negative 4t. So let's put those together. So negative 1/2 c1 e to the negative 4t. And then y of t we did earlier. We said that was c1 e to the negative 4t. And I know this is a bit confusing. We definitely will do some practice and go over this procedure again in class. It'll make a little bit more sense. But this is going to be my general solution to the differential equation. So bring your notes with you and I'll see you tomorrow in class.